Hello, this is a video to show the proof of the existence and uniqueness theorem. So in the previous video we gave a general overview, and now we want to go through the 4 steps, step by step, to figure out if we can prove them. So this is the rectangle in which we have that f and df dy are continuous. So we have t0, y0 at the center, and for all t's between minus a, and for all y's between minus b and b, we know that f of yt and df dy of yt are continuous, both of them. So within this rectangle, the integral f(ty) dt is well defined. But if we replace y by phi n t, this integral is well defined only if phi n t is in the rectangle we just defined. So if you want to look at it, you can imagine that if phi t wiggles within the rectangle, then we're good. But if it has to, remember, it has to pass for t0, y0. But if it just jumps away from the rectangle, then we have to restrict ourselves to a smaller section. We have to bound t a bit tighter in order to always have the result of our integral. Phi t could just be fairly tame outside the rectangle, but we don't know if f is. What we know is f is continuous only within this rectangle. And df dy is also continuous only within this rectangle. So integrating outside of this rectangle is a problem. So we need to restrict our rectangle to be sure that phi n is within it. Would we still have something? Well, let's look at it a bit more carefully. We know that all phi n's at 0 are at 0. So anything that passes through that rectangle actually has to pass by the point 0, 0. Then we also know that phi prime is equal to f of t phi n minus 1. But f is continuous in R. So it is also bounded in R. We assume that it is bounded in R by m. So phi n prime is bounded by the same value that we introduced, we called it m, in the whole rectangle R. So what it means is that phi prime cannot jump too fast because we know that it's bounded by m. If phi prime cannot jump too fast, it means that phi is restricted within a rectangle, within a triangle. We know that it has to pass by 0, 0, and we know it cannot get over a certain triangle because its derivative is bounded. So we know that phi n must lie between this y equals mt and y equals minus mt on both sides. So we know the area in which phi n must be. If m is too steep, then we have to restrict our rectangle. So push a closer by such that phi n cannot escape from the top. But if m is small enough, then we can keep everything. So phi n exists for all n if we restrict t at cases. So we know that the sequence exists. Does the sequence converge? I'm going to leave this as an exercise problem, but I'm going to give you a spoiler, it does. It does, and we call phi t the function it converges to. So what we're taking is the limit for n tending to infinity of a function phi n. And we say that this limit exists for t in a certain neighborhood, from t0 minus h to t0 plus h. This limit exists. And we call this limit phi t. Does it converge to the right thing? Is the next question we want to ask. So we know that each step of our sequence we have phi n plus 1 equals integral from 0 to t of f as phi n ds, phi n function of s ds. By the definition of the limit function, we know that phi t, the limit function, is equal of the limit for n tending to infinity of this integral. We would like to get the limit inside the integral. Is it possible? Can we do that? We cannot always do this, but we can do it when we know that phi n converges uniformly to phi. The brief version of this slide is phi n converges uniformly to phi. You don't have to worry about it. But this slide is here to explain you what it means to converge uniformly. It's written optional in the sense that other than the quiz referred to this video, no other quiz ever will ask you to know the difference between uniformly and other forms of convergence. But what is the idea of uniform convergence? It means that in the interval in which a convergence happens, you can fix an error epsilon, and there is a value n that depends on epsilon, such that for all k's bigger than n epsilon, the maximum error you're making between computing phi and computing phi k at any value of t in your interval is smaller than epsilon. It means that if you fix a mistake, then you can just wait enough iterations and everywhere in the interval you fit within that mistake. It's a pretty strong information. It means that everywhere in the interval, phi n converges to phi roughly at the same speed. The uniform convergence is a pretty strong statement. The weaker version of it is pointwise convergence. So we know that we say that phi n converges to phi pointwise if you first fix a t, then you fix an epsilon, and for any combination of t and epsilon, there is a value n such that phi k computed at t minus phi computed at t is smaller than epsilon for all values of k bigger than the n epsilon t. Why is it different from the uniform convergence? It's different because here you might have to wait more iterations of your sequence depending on where you are in the interval. So you can think of the fact that if you are somewhere at a specific time, then you have to wait only a couple of iterations before converging, being epsilon away from the exact solution. While for the same epsilon somewhere else, you might need to wait way longer. This pointwise convergence is problematic at times because it might mean that if you're creating sequences in the wrong way, some points will take forever to converge compared to other points that already converged. That's why uniform convergence is so much stronger. Luckily, in our case, we have uniform convergence, so we can shift the limit from outside of the integral to inside the integral. So we're good. The next step is we wonder, can we shift the limit from outside of f to inside f? This happens only if we know that f is continuous with respect to the second variable. And this is true by assumption. We have required f to be continuous in the whole rectangle, and phi ns is within the rectangle, so we're good. We can move everything inside, then we replace the limit for n tending to infinity of phi n by phi, and we have proven that if you construct a sequence in the way we did, then it converges, and the convergence is the solution to the integral equation. Therefore, it's a solution to the ODE. We have proven existence. Is it the only solution? is the next step of our problem. Can we prove uniqueness as well? Obviously we can. And we start that by a standard approach when we want to prove that there is only one. We assume the existence of a second solution. We assume the existence of the solution psi. So phi t is the solution of the integral equation. Psi t is also the solution of the integral equation. Can we prove that they are the same thing? If we prove they are the same thing, then any other solution that you find is always the same. So we only have one solution. Let's try to do that. We first subtract the two things. So we have phi t minus psi t equals integral of f s phi minus f s psi. Then we bound things. We take absolute values on both sides, and we bound phi t minus psi t by k integral of absolute value phi minus psi. K is a bound on the second derivative of f, on the derivative of f with respect to a second variable. So it's how much f changes if you're changing the second variable. In order to prove that there exists only one solution, we introduce a function u of t that is exactly this integral. So it's the integral between 0 and t of phi minus psi ds. Because it's the integral of an absolute value, then we know that ut is always positive for all t. And we also know that u computed at 0 is equal to 0 because it's an empty integral. It's the integral of something between 0 and 0. We also know that y prime is, well, by the fundamental law of integration, we can take away the integral. So y prime is the absolute value of phi t minus psi t. From the equation we had before, we have that phi t minus psi t is bounded by k integral from 0 to t of phi minus psi ds. And by what we introduced, one is y prime and the other is k times u. Doing some shifts around, we notice that we can write this as e exponential of minus kt times u, function of t, all of this derivative with respect to prime, with respect to time. And we know that this is bounded by 0. So with integration and knowing that u of 0 is equal to 0, we know that the exponential of minus kt multiplied by ut is bounded, is smaller or equal than 0. But we have that exponential of something times u is smaller or equal than 0. But we also know that u is bigger or equal than 0. Now, the exponential of something is always positive. So what we are stating is that u is both smaller or equal than 0 and bigger or equal than 0. So the only solution is that it must be exactly 0. But ut is defined as the integral of the absolute value between the difference between the two possible solutions. So we have proven that the two solutions must be equal all time. So we have proven uniqueness as well.